IEEE Computational Intelligence Society webinar. My name's Keely Crockett and I'm so delighted and excited to introduce Professor Giovanni Acamporo from the University of Naples. Basically, he's a professor of artificial intelligence and quantum computing at the Department of Physics. His research focuses on computational intelligence and quantum, and he's the current chair of the IEEE SI 1855 working group and editor-in-chief of Quantum Machine Intelligence. No doubt he's going to share with us some of his background and his wonderful research. So without further ado, I will hand over to you. And we're very excited.
Thank you, Keely. Yeah, first of all, I would like to thank you, Keely, and I would like to thank IEEE Computational Intelligence Society, particular Joel and Tom, for having organized this webinar on this emerging topic, merging together two different areas of computer science, quantum computing and computational intelligence. And I will give you a kind of wide overview about this topic. I will introduce you with the motivation about we have to deal with this new topic in computational intelligence. I will provide you some fundamentals of quantum computing, and I will give you some examples of a combination of quantum computing and computational intelligence by discussing about quantum fuzzy system, quantum genetic algorithm, and quantum neural network. And at the end of the webinar, we will discuss also about the role of computational intelligence for the design of quantum computers. So now we can start with the introduction, where we will discuss about computational intelligence and quantum computing. Everyone knows what computational intelligence is a set of nature-inspired computing methodologies such as neural network, fuzzy system, and evolutionary algorithms, and their combination. In particular, we know that fuzzy logic is a kind of logic that unclassical binary logic use membership degree to work, and it allows us to work with linguistic rules and fuzzy systems. Then we have genetic algorithms that are optimization algorithms useful to find approximate solution to hard problem, and they are inspired by Darwinian evolution and genetic process of natural selection. Then at the end, we have neural networks as algorithms used to perform classification and prediction by implementing learning mechanisms. So at the end, we can say that these three methods, the three computational intelligence methodologies, belongs to different three areas of artificial intelligence: reasoning for fuzzy system, learning for neural networks, and problem solving for genetic algorithms. So it can be viewed as a kind of unified approach for designing enhanced intelligence system. They are a kind of complementary and diverse methods that implement value aspect of AI system. But even though they are different, they can be as they share a fundamental trait. They can be implemented by algorithm running on digital computers, and it means that they can be run by algorithm that can be computable on Turing machine. And from a practical perspective, this algorithm can be implemented properly on von Neumann-based computers. So it means that fuzzy logic, genetic algorithms, and the neural networks share the same computational foundation based on Turing machine and von Neumann architecture. Okay? But now something is changing. Quantum computing is starting to become a kind of reality in computation. So in the future, maybe we will add new computational foundation to the classical foundation. And the question is how this new computational paradigm will influence the development and performance of computational intelligent techniques from one side. And on the other side, we would like to understand how quantum computing will interact with computational intelligence and what novel approach might emerge at intersection of these two fields. So in order to explain you what are quantum fuzzy system, quantum genetic algorithms, and quantum neural networks, I have to introduce briefly with the basic concept of quantum computation and the motivation to move from classical computation to quantum computation. In order to start with this discussion about the motivation, we have to say that today the word quantum is used in everyday language to refer to objects or services that are characterized by enhanced capability. Just as an example, if you try to search on Amazon the word quantum, you can find the quantum shoes, the quantum detergent, or the quantum headphones. So now it seems that everything is quantum is better. But why? Quantum has become synonymous with improvement, efficiency, and added value. In order to answer this question, we have to remind what a classical computer is. A classical computer is a programmable automated system that uses the theoretical computational model of the Turing machine and architectural framework of von Neumann to work. And in particular, it uses these two models, and the von Neumann architecture uses Boolean algebra to design some operating principle of electronic computer. So we have that in the classical world, the two models to use are Turing machine, von Neumann architecture, and the mathematical structure on which classical computers are based is Boolean algebra. Okay? What is the history of modern computer? The history of modern computer is from 1971, when Federico Faggin, an Italian scientist, introduced the microprocessor, transistor-based microprocessor with Intel 4004. This microprocessor was equipped with around 2000 transistors with a very low frequency, and it operated on the data at 4 bits. This is the architecture of this processor. But thanks to the miniaturization of transistor, the power of microprocessor has increased exponentially. We moved from few operations per second to billion of operations per second, and now we have billion of transistors equipping the modern microprocessor. So the miniaturization of transistor allowed us to improve the performance of our system. And moreover, our classical computers are very good because we can equip them with additional devices such as GPUs or FPGAs that can support microprocessor in hard calculation. And so the question is, why consider an alternative computing approach to the Turing machine and von Neumann model when we already have access to a very powerful computational system based, for instance, on GPU and FPGAs? There is no reason, but the reason is related to the Moore's law. Gordon Moore was a founder of Intel, and he theorized that the number of transistors in a microprocessor would double every 24 months. And this law is true. But what it means? It means that now the transistor is reaching atomic scales, where classical physics no longer fully applies and quantum mechanical effect became dominant. And in this context, quantum phenomena can significantly alter in a bad way the behavior of transistor, and these could pose challenges to the stability and reliability of classical computer. So we cannot further reduce the size of transistor to improve the performance of our classical computer. But in 1981, Richard Feynman, a Nobel Prize for Physics, recognized that a classical computer was not able to simulate efficiently a quantum system. And he thought, if we introduce a quantum computer, maybe this computer is able to not simulate, but implement in a direct way a quantum system, and for this reason it is better to perform this task than a classical computer. And so the first idea of a quantum computer was related to this guy, Richard Feynman, and it was about the simulation of quantum physics. And during the year, starting from that year, this idea grows until in 1994, Peter Shor introduced the first quantum algorithm that was better than its classical counterpart. This quantum algorithm was related to the integer factorization problem. It was a polynomial algorithm on quantum computers, but its classical counterpart on classical computer was exponential. So we had the first example of a theoretical quantum advantage in 1994. And another example is related to the Shor's algorithm, that is an algorithm to search item in a list. On a classical computer, the computational complexity is linear, but on a quantum computer, the computational complexity is a square root of n, where n is the number of items that we would like to search our element. Okay? So these are the first two examples of algorithm proving a kind of quantum advantage. And thanks to these two algorithms, we can say that quantum computer pose a serious challenge to the strong charge Turing thesis. What says this thesis? It says that any physically realizable computation can be efficiently simulated by a digital classical computer. It means if we are able to build an alternative kind of computer based on quantum aspect or biological ideas and so on, we can simulate this computer in an efficient way by using classical computer. But however, because we have the Shor's algorithm, the Groover algorithm, and other examples of quantum algorithms that are better on quantum computers, it could be that quantum computation could represent a potentially superior computational model than the computational model based on Turing machine and von Neumann architecture. And so this is the reason why we are talking about quantum computing in every place now. What are the principles that allow us to work with the quantum computer? These principles are superposition, entanglement, and interference. So we have these three principles that are specific to quantum mechanics that we cannot use in classical computer, and that can allow us to implement, in our case, artificial intelligence methodologies in a more efficient way than classical computation. But how a quantum computer works? When I was young, when other professors introduced me with the concept of classical computer science, they used the concept of light switch to represent the bit, the binary digit, 0 or 1. We can say that a qubit, that means quantum binary digit, the basic element for representing quantum information, also can be seen as a switch, whose state is identified by a point on a three-dimensional sphere. And at the pole of this sphere, we have the classical state, the classical bit 0 and the classical bit 1. So for instance, in this case, we have a state of our qubit that is closer to 0 than 1. So, but if we think in this way, we can say that we solved all the problem in computation, because I need only one sphere to store infinite information, because this sphere has infinite points on its surface. And for instance, I can store the whole internet on this sphere by relating each point on the sphere with a URL address. But unfortunately, this is not the case, because we cannot read this value. We cannot read the point on the sphere. When we look at the qubit, the state will collapse to 0 or 1. And this is the first limitation of quantum computation. From one side, we have a benefit because we can store a kind of infinite information, but we cannot read it directly. Okay? How is it possible to manage a qubit from the mathematical point of view? The state of a qubit, this symbol named ket psi, can be viewed as a linear combination between 0 and 1. Okay, between the two basis states 0 and 1, where alpha and beta are complex numbers named amplitude, whose squared modulus represent respectively the probability that the state psi will collapse to 0 or 1 after the measurement. So when we look at a qubit, when we measure a qubit, we start a kind of statistical, stochastical process where the state of the quantum bit will collapse to a classical bit with this probability. But what are these symbols? What is the ket symbol? This symbol belong to the so-called bracket notation or Dirac notation, is a different way to represent vector. Okay, so we are working in this case with vector. A qubit can be represented by using a linear combination of two vectors, where this vector represents the classical bit 0 and this vector represents the classical bit 1. So for this reason, we are moving from the Boolean algebra as a mathematical structure related to the classical computation to Hilbert vector space that are a particular case of complex vector space that regulate the behavior of quantum computers. So the first difference between classical computer and quantum computer is related to the mathematical structure used to work with them. Now, we can understand in this slide one of the first benefits of using Hilbert vector space to make computation. Because if we consider a single qubit, the base states, the pole of the sphere, are 0 and 1, and the generic state is alpha 0 plus beta 1. It means that a single qubit needs two complex numbers, represent two complex numbers. If we consider two qubits, the base states are all combination of two bits, 00, 01, 10, 11, and the generic quantum states is alpha 0, 00 plus alpha 1, 01, and so on. So with two qubits, we are able to manage four complex number. In general, with n qubits, the state of our quantum computer is composed of 2 to n complex number. So you can see that the number of information that we are able to embody in a quantum computer is exponential with respect to the number of its basic component, the qubit. With n qubit, I store, or better, I embody 2 to n complex number in a quantum state. Thus, in a classical computer equipped with n bits, the mathematical reference structure is the Boolean algebra that allows us to define state characterized by a sequence of n binary digits. So, in a in a quantum computer equipped with n qubit, the mathematical structure is the Hilbert vector space that allows us to define state characterized by a sequence of 2 to n complex number. So a quantum computer is able to store in a single state more information than a classical computer. But as we know, we have to implement algorithm on these machines, classical or quantum. And from the mathematical point of view, these algorithms on classical computer are implemented by using function mapping binary string to binary string. Okay, so all the algorithms are implemented by using and, or, not, and so on operator of digital logic, and they can be viewed in this way. On a quantum computer, we use linear transformation between the complex vector space C to 2 to n and itself. So when we change the state of a quantum computer, we are changing 2 to n complex number by means of this kind of function. But because this function is a linear transformation, it can be implemented by a matrix product. So the basic operator working on quantum computers are metrics. Okay? And in this slide, we see an example. These are, we cannot go into the detail, but however, we have a list of operator, the quantum operator, represented by this gate, that implement this operation. So when I implement the Hadamard gate, I have to multiply the current state of my computer, or my quantum computer, by this matrix. And at the same way for this other operator. And by means of this operator, I am able to change 2 to n complex number in a single computational step. This is due to a particular principle of quantum mechanics named quantum superposition. But however, there are other effects, quantum effects, that allow us to work with quantum computer in a potential better way than classical computer. The first example is the quantum entanglement, which create a kind of strong relationship between two qubits. And when we relate two qubits among them, these are all the action on the first qubit act on the second qubit too, and this allows us to increase the level of parallelism in our system. Then we have the quantum interference. As I said before, the value alpha related to each basis status of qubits or a quantum register in general is related to a distribution, to a probability distribution. And the quantum interference is a particular concept of quantum mechanics that allow us to change the value of this probability distribution in a single step to reduce the probability to get wrong result when we run our algorithm and increase the probability to get right result when we run our algorithm. So superposition, entanglement, interference are the three basic concepts that allow quantum computers to work potentially better than classical ones. So this is just an example. This is a quantum circuit implementing an algorithm, and typically an algorithm works in this way. The system will start with qubits in a particular classical state. Then we create a superposition of many states, and we work on this superposition by using unitary operation, the multiplication but by matrices. Okay? And at the end, if we perform this, because the output is a kind of stochastic output, we have to perform multiple runs of the same algorithm to get this output, a probability distribution that we have to work with in order to compute the final result of our algorithm, depending upon the problem that we would like to solve. So, as I said, using superposition, entanglement, interference, quantum algorithms are capable of producing a potential computational advantage over the classical counterpart. And this suggests that quantum computing may be not efficiently simulated by a classical computer, and it may invalidate the strong charge Turing thesis. That is a very important theoretical result. But how quantum computers are built today? There are different technologies to build quantum computers: superconducting qubits, photon qubits, trapped ions, and solid-state qubits, and so on. But however, we have to say that independent from the technology, we are living now the noise intermediate scale quantum era, which refers to the possibility to build quantum computers that are characterized by a low number of qubits. They are very small computers, but these qubits are characterized by computational noise. So currently we have small quantum computers and not reliable quantum computers. So this is a problem that, for instance, computational intelligence can try to solve, as we will see later. Okay, now that we have completed our overview about quantum computer, we can go into the details of the combination of computational intelligence and quantum computation. In particular, I would like to start of fuzzy systems. We know what fuzzy systems are. They are a class of systems based on fuzzy logic that allow us to control a system, the relationship between input and output of a system by means of linguistic rules that are based on fuzzy term and linguistic variable. So we are able to write the control of our system by using these rules, for instance. And this is the classical view of a fuzzy system. We have the knowledge base composed of variables and rules, we have the falsification interface, and we have the fuzzy inference engine that perform the set of fuzzy operator to transform the input into the output. Yeah? So everything seems okay, but why I have to think about quantum fuzzy system? Because we could have a problem with fuzzy system named fuzzy rule explosion. Indeed, if we suppose to have a system with n input variables, each modeled using m fuzzy set, then the maximum number of fuzzy rules described such a system is m to n. So a system is potentially controlled by an exponential number of rules. So if we run a conventional Mamdani inference engine or TSK inference engine, we have to evaluate an exponential number of rules. So the computational complexity of this algorithm is exponential, and quantum computers can potentially improve this running time. Indeed, our idea is to try to perform the computation of fuzzy rules in parallel on a quantum computer. And in 2022, during the PhD program of our researcher Roberto Schiattarella, we introduced an algorithm named Quantum Fuzzy Inference Engine that uses a concept named Quantum Oracle to model fuzzy rules and enable the quantum design of a fuzzy inference engine. Later, I can share with you this slide, and here you can find the code, the source code of this algorithm, and the reference paper for this algorithm. And thanks to this algorithm, we change our vision of fuzzy system for a classical vision to a quantum vision where we have a quantum oracle to perform the inference. But how this oracle work? In order to explain how this oracle work, we have to consider, for instance, some variables, two input variable of a system, pedestrian density, vehicular traffic, and the output variable street light brightness. We have to label each membership with a binary value, for instance 00, 10, 01, 11, using the conventional binary representation for the input variable, and we have to use the one-hot encoding representation for the output variable. So in this way, if we perform this labeling, I can create a function f that relates the Cartesian product of this label corresponding to the input label with the output of the system. Okay, so by means of this function, I can model this rule. For instance, if pedestrian density is high, then vehicular traffic is high, then street light brightness is high, by means of this function. Okay, because I have to relate 0, 0, because high is 0, 0, to 1, 0, 0, 0. So I have a binary way to represent our fuzzy rules. And the idea is to use this function to implement our circuit. Obviously, now I cannot go into the detail of the circuit representation, but we have to know that this function corresponds to these quantum circuits. So by means of this function, I am able to put a fuzzy rule on a quantum computer. And the set of rules that I get in this way is named UF. That is a matrix that multiplied by the input of the circuit perform the fuzzy inference, as we will see here. So in this case, we have two quantum states. This is the quantum state related to the first variable, the quantum state related to the second variable, and this is similar to the states we saw before when I introduced the qubit, but for each value 0, 0, 1, 0, 0, 1, and 1, 1, we have the fuzzified value of each binary string corresponding to a fuzzy set. So I am storing in this quantum state the fuzzified value of the system. Now, when I put together two variables in a native way, a quantum computer performs the tensor product between these two quantum states, psi-PD and psi-BT, and this allows us to calculate the antecedent part of each rule, because we have, for instance, the rule low, low, the rule low, medium, low, and so on. So we have all the antecedent part computed in a single quantum step. Okay? So in order to calculate the output of the whole system, I have to multiply the circuit related to our rule by this state. Okay? Multiply my rule by this state allow me to perform the inference. Okay? At the end of the inference, as I said before, I will run the algorithm more than one time. I will get some probabilities related to the different strings in my system, and I use these probabilities to cut the output fuzzy set and perform the defuzzification at the same way we do in the classical system. Now, from the computational point of view, I can say that in the classical world, we have a computational complexity that is exponential. But as you can see in this slide, and you can read in our paper, we have a computational complexity linear to perform the fuzzy inference operators. That is linear in terms of oracle queries. Okay? So this is just to say that we improve the performance of a fuzzy system from the computational complexity point of view. Okay? Now, from this study, we can introduce a new concept, quantum computing with words, at the same way the father of fuzzy logic did in the 60s and 70s, because we have a linguistic fuzzy rule base. We are able to model this linguistic fuzzy rule base as a quantum circuit, and we can run it on a quantum computer. And in this direction, we increase the efficiency of fuzzy system. But as you can know, the quantum computer is very hard to program. You need knowledge about complex vector space and so on. But in this case, we are programming a quantum computer with linguistic rules. So moving from here to here, we are increasing interpretability in quantum computation. So thanks to our QFIE, we are able to reach both goals, interpretability and efficiency. We implemented this approach in different application domain. For instance, we controlled the particle accelerator at CERN in Geneva. We used this rule to control an inverted pendulum. We used this approach to control smart city, and thanks to this approach, we have been awarded with a Fujitsu Quantum Challenge award, and so on. So QFIE work good on quantum computers. Now we move to the second part of the quantum computational intelligence, where we introduce genetic algorithms. Okay, what are genetic algorithms? Genetic algorithms are algorithms where iteration after iteration, candidate solution move towards the target states of one problem in a potentially parallel way, in a kind of pseudo-parallel way. And a quantum algorithm, our idea is that a quantum algorithm can perform this genetic evolution in a quantum way by using matrix multiplication, as we said before. And in 2021, together with our collaborator Autilia Vitiello, we introduced a new algorithm that is the first genetic algorithm implemented on a quantum computer, named the hybrid quantum genetic algorithm, where all the evolutionary steps of a genetic algorithm are performed on a quantum computer, but the fitness evaluation is performed on a classical computer. In particular, this algorithm embodies M genetic chromosomes, M genetic population in M quantum register, and it uses the entanglement among the quantum register containing the current best classical solution and the remaining one. And it performs mutation by rotating some qubits. It means that rotate the arrow in the sphere. So by means of these operators, as we proved 4 years ago, it is able to show a kind of convergence towards suboptimal solution of a problem on a quantum computer. I show you just some example of the circuits we used, for instance, to create the population. For instance, we have this is a quantum register. When we perform this operation, Hadamard and RY operation, we are creating a kind of probability distribution containing different classical solution of our problem. The idea is that with the quantum entanglement and the quantum mutation, we are able to increase the probability to read a good suboptimal solution. This is the circuit related to the quantum crossover. It is performed by using, it is designed by using some CNOT gate, that is the gate implementing the entanglement. In this case, you can see here that this register on a quantum computer corresponds to the current best solution. So we relate these qubits to other portion of other population. So we are moving, thanks to this operation, genetic material from a quantum register to another quantum register. This is a simple rotation that implements the mutation of genetic algorithm. Okay? Then this algorithm is also equipped with a kind of elitism. In particular, we have implemented 3 different kinds of elitism: pure quantum elitism with reinforcement, and deterministic elitism. And in this case, you can see an example of elitism based on pure quantum approach. Then we applied this, when we designed this algorithm, quantum computer were equipped with just 5 qubits. And so the problem to solve were very, very small. So we tried to solve the 1 max problem on a real quantum computer. These are the different iteration, the different evolution of our problem, and you can see how the average fitness value increase. Okay? So even though with this small problem, we have this proof of, not proof, but this kind of example of convergence. Now that quantum computers are increasing in terms of their size, we would like to test this algorithm in order to prove its potential benefit on real-world problems. Then behind the HQGA, a complete quantum algorithm performing the evolution of genetic population on a quantum computer, we have also implemented some quantum operators. In particular, we designed quantum operators to use in a classical genetic algorithm. For instance, we introduced the quantum genetic sampling, that is an approach used to replace the selection operator of classical genetic algorithm in order to increase the diversity of population. Or we have also introduced the quantum mating operator that replaces crossover and mutation in a classical genetic algorithm. And we applied the quantum mating operator in different application domains, such as, for instance, the control of traffic lights. So we have different strategies to implement quantum genetic algorithm. You can think about a whole, an entire new algorithm, or you can replace some operator in classical genetic algorithm. Okay, now the last part is related to quantum computational intelligence, in particular neural network. We would like to know how to implement neural network on quantum computers. Okay, what are neural networks? We know that neural networks are a methodology belonging to machine learning that, starting from historical data, are able to provide some prediction capabilities. In terms of quantum neural networks, they are exactly the same things, but they use quantum circuits to implement the learning. So from one side, we have this neural network. On the other side, we have a quantum neural network implemented with a quantum circuit, within terms of the gates we show in the previous slide. How these networks are implemented? They can be implemented in two different ways. From one side, we have the idea of quantum perceptron, that is a quantum way to simulate the biological neuron from the point of view of the behavior. From the other side, we have variational quantum circuits that are quantum circuits equipped with some free parameters to be tuned to implement learning tasks. So it is very, very similar to conventional neural network where we have weights, but in this case, we have gate parameters. We have to train, we can train a quantum neural network by identifying the right set of parameters. What are the benefits? As I said before, the main benefit of quantum computation is to work in high-dimensional spaces. With n qubits, I am able to work with 2 to n complex number. So with n qubit, I can work with 2 to n parameters of my quantum neural network. And in this way, I can try, for instance, one of the goals is to try to improve the performance of algorithm for training machine learning models. So this is the classical vision of machine learning. We have training data used to teach a model by learning patterns from examples. We have the model, the system that learns from training data to recognize patterns and make prediction. We have the cost function used to measure the error between the model's prediction and the actual values, and it is used to guide the optimization by means of the computation of gradients. Computation of gradients means calculating the rate of change of the cost function with respect to model parameter to perform the optimization of the parameter in the model. Okay, so this is a very general view of machine learning. How this approach change in quantum machine learning? This approach change in quantum machine learning because in quantum machine learning we have to consider 4 combinations. when we talk about quantum machine learning, we have, or in general also about machine learning, we have to consider this combination. For instance, if we have classical data and classical algorithm, we are in this place where the pure machine learning lives. Okay. In other case, we are here where we have quantum algorithm and classical data. That is the most used approach of quantum machine learning today. Here we have quantum data and classical machine learning approach. Here we have quantum data and quantum algorithm. Currently, this is the most used approach where we would like to improve the performance of machine learning method working on classical data by using quantum algorithm. How we try to perform this action? We perform this action by replacing the classical model with a variational circuit. Okay? This is a so-called variational circuit because this quantum circuit depends upon the theta parameter. Okay? So this is a parameterized quantum circuit, named also variational circuit because its behavior change depending upon the value of this parameter, and the shape of this circuit, the way how the different gates are located in this circuit, is named ansatz. Okay, so in our machine learning, in quantum machine learning, in the most simple case, we have to identify this parameter. But there are some cases where we can also identify the ansatz, the location of the gate on this circuit. But there is a problem, okay? What is the main problem with quantum machine learning? The main problem with quantum machine learning is the so-called Barren plateau problem. What means? It means that in deep quantum circuit, when the size, the depth of our quantum circuits strongly increase, gradients vanish exponentially. It means that we are not able to guide the optimization of parameter in a proper way, making the training infeasible. Okay? And so, what is the reason? It is related to random initialization of parameters, or in the quantum case, excessive entanglement spreading information across too many qubits. It's a kind of pure quantum problem. But it means that traditional gradient-based optimization, such as ADAM, SGD, and so on, becomes inefficient. For this reason, as a computational intelligence community, we have to think new approaches to train this kind of circuits. And in our research, we could think about evolutionary algorithms. Why? Because they are gradient free, so they do not suffer of vanishing gradient, and they are able to efficiently move in hard landscapes. Okay? What is the training strategies? We can, for instance, instantiate a population of quantum circuit parameter, this theta parameter, implement mutation and crossover of this parameter, of this set of parameter, and to perform the selection based on the fitness, for instance, the classification accuracy of this circuit. Which kind of algorithm we can use? Every kind of evolution algorithm we know in literature, from genetic algorithm to particle swarm optimization, and so on. And in our research group, we have introduced a Python library implementing this task in a very simple way. In a very simple way, as we will see in the next slide. This slide shows another example of difference between the classical machine learning and quantum machine learning. In particular, when data are classical, in this case we have a dataset D of classical data. In order to introduce a classical dataset in a quantum computer, we have to perform a so-called encoding. This encoding could be basis encoding, amplitude encoding, and angle encoding. You can deep knowledge about this encoding scheme by yourself later. Then we can apply a parameterized model we can measure the circuit to extract the labels, and we can use evolutionary optimization technique to update the model parameter. So this is the scheme used to train a quantum machine learning algorithm by using evolutionary optimization techniques. And as I said before, this approach has been implemented by our research group. In this case, I forgotten to write that this library was developed by Angela Chiatto, that is a current postdoc in our research group. The name of the library is Evolutionary Algorithm-Based Toolbox for Variational Quantum Circuit, developed by a collaboration between University of Naples, Federico II, and the University of Granada. And together we have implemented this library with the main activity performed during the PhD of Angela Chiatto, and we published this library on Software X. And you can see here in this slide how this library can allow us to simplify the training of quantum machine learning model, or in general the training of a variational quantum circuit by means of very simple Python function. So if you would like to work with quantum machine learning and evolutionary algorithms, you can download this library from this GitHub link. Okay, so now I have introduced you in a very quick way. I would like the idea was to give to you a kind of a wide overview about quantum fuzzy system, quantum genetic algorithms, and quantum neural network to allow you to understand that this research field is going on. There are some quantum implementation of different computational intelligence methodologies such as fuzzy system, genetic algorithm, and neural network. So in this part of the presentation, we saw that quantum computing can help computational intelligence. But we have another question. Can computational intelligence technique, the classical computational intelligence techniques, support the design of the future generation of fault-tolerant or reliable quantum computers? This is the question that we would like to answer in this slide of the presentation, where we highlight what are the current issues in quantum computers today. In quantum computers today, we have noisy operation. It means that the gate, the matrix operation that we perform in our quantum computer are characterized by errors. We have unlimited qubit connectivity. So all the qubits in a quantum processor are not connected among them. So it could be hard to perform some operation involving 2 or more qubits. Then we have scalability challenges. It means that it could be very hard to build computers characterized by a higher number of qubits. And we have other problems such as error correction overhead. It means that from the engineering point of view, researchers are trying to solve the error problems in quantum computers, but to solve error problems in quantum computer, they have to use many physical qubits, okay, that are not useful for solving real-world problems because they are used to correct the error in computation. And for this reason, due to these issues, as computational intelligence community, we can work together to identify some strategies to improve and to solve these issues, such as, for instance, approaches based on computational intelligence for quantum error mitigation and correction, approaches based on AI and machine learning for efficient qubit mapping and compilation, and artificial intelligence approach for adapt quantum algorithm to specific device constraints. So there are several quantum issues that classical computational intelligence methodologies can try to solve. So this field is open, is very new, and there are several problems to solve, in particular with respect to quantum error mitigation. In 2021, together with Autilia Vitiello, another collaborator of our laboratory. We have been awarded with a best paper in fuzzy IEEE 2021, where we used the fuzzy clustering, a kind of approach, a framework based on fuzzy clustering to try to correct error in IBM quantum computers. And when computers were very small, we were able to improve the performance of this computer by using fuzzy clustering. We tried to solve the same problem by using genetic algorithm. There are other guys solving the same problem with the neural network. So there are some problems that you can solve with classical methodologies for quantum, for improving the performance of quantum computers. Now we arrived to the conclusion, where I would like to say that quantum computational intelligence is not a utopia, is a real research field where there are several opportunities for exploration and innovation. There are potential for introduce novel algorithms for fuzzy logic, genetic algorithms, and neural network. And also there are potential to develop innovative computational intelligence approaches to support the design of reliable quantum computers. And I would like to finish my presentation to say that quantum computational intelligence, or more in general, quantum artificial intelligence, is a kind of reality today because IEEE decided to start the IEEE International Conference on Quantum Artificial Intelligence that we will organize in the next November in Naples. The website is currently under construction, but from the next week, you will have all the information about this conference that is the first IEEE conference on this new emerging topic. So, thank you very much.
Thank you so much as well. And I definitely recommend you follow Giovanni as well. His LinkedIn profile is on there as well. Thank you for the most enlightening presentation. I mean, I can't even begin to say how brilliant it was. But we have a number of questions and we have some minutes. I'm going to go right back. So I will try and summarize some of the questions. There is a lot. We're not going to get through them all. So I'll also refer to the time it was posted in the chat, just in case you want to reread. So I'm going back to a kind of an early question. It was about slide 26. And at 1517, the question was all about 26 states are two-dimensional while the space you represent is 3D. Can you clarify, please?
Yeah. Okay, it is not so simple to move from, in this slide, to move from here to here. Okay, formally, this slide is named block sphere, is a kind of graphical view to consider a quantum state. But however, it is very strange because in order to identify this point on the surface, we need two angles. Okay, we need these angles and this angle. Okay, we need two angles, two real values. But if you see here, the quantum state is composed of four real values because we have the real part, the imaginary part of alpha, the real part and imaginary part of beta. However, exists a mathematical demonstration that allows us to put these four numbers on this sphere, to transform these four numbers in a pair of angles on this sphere. So you have to check on some quantum computing book the demonstration, but however, thanks to the exponential form of complex number, we are able to move these four numbers embodied in alpha and beta into angles to move the arrow on the sphere, on the block sphere.
Okay, we have one at 1533. Could we ever use quantum computing to predict human behavior better than classical AI?
Okay, these are very, very open and visionary questions. It is important to have this question, but we have to understand now we are in a very pioneering, in a very embryonic phase of quantum computing. We are able to solve little problem. We are able to implement very simple quantum machine learning model because, as I said, quantum computers are not so ready for real-world application. For instance, as said by NVIDIA CEO 2-3 weeks ago, maybe in 15 years, we will have a real practical quantum computer. But today we are not ready to answer to that question, but I think that we have to work now to be ready when quantum computers will be available. So it is an important question. If you want, you can start to work on this topic to solve very little problem in this area, but when quantum computer will be ready, maybe you will be ready to implement this algorithm on a real quantum computer.
Thank you so much. There's more technical question from Michael at 1547. He's combined a number of questions in there. And he says, when working in an N space require even more computational power, or working in N space increases efficiency? And he asks, is there a measurement of computational efficiency for a way to compare methods? Yeah, I'll start with that one.
Okay, about the computational power and the space is related, I think, to this slide. So we do not need more computational power to work in this way, but in this mathematical structure. But is this mathematical structure that allows us to have an increased computational power. Because with, as I said before, with one qubit, I am able to store two complex numbers on a computer, on a quantum computer, alpha and beta. If we move to to 2 qubits, we have 4 quantum states, basis quantum states, and we are able to store alpha 0, alpha 1, alpha 2, and alpha 3 on a quantum computer. In general, if I use n qubits, I am able to store 2 to n classical complex number. Okay? And when I act on this state, on this exponential number of complex number, I am changing them in a single step. So by using this mathematical structure, I am able to change and to modify step by step an exponential quantity of information. So, yeah. And the other question was? Okay.
Michael goes on to say, as problems are more complex, does the power needed to solve these problems at times grow exponentially? There is a logistic function perhaps that will imply there'll never be a solution to a given complex problem, no matter which quantum computing algorithm you use. And can we classify these types of problems?
Yeah, this is how to say, not simple to go into this detail now, but yeah, there are. When I talk about quantum computer, I always said potential advantage. Okay, so maybe there are some things that quantum computer will be able to solve, and other things that we can do better with classical computer. So we are not saying that quantum computer will solve any kind of problem and they will replace classical computers, but maybe there are a kind of group of problems that will be solvable on a quantum computers better than a classical computer.
Okay, and I've probably got time for one more. There's quite a few questions, and I'm so sorry that we haven't got around to all of them. In your fuzzy work, you mentioned that an efficient solution. What was the efficiency you could highlight?
Okay, when we discussed about the efficiency of the fuzzy system, we discussed about the quantum oracle. Quantum oracle is a kind of design pattern to implement quantum algorithms. There are several quantum algorithms based on quantum oracle. That is a kind of function where you can ask a question and the oracle give you the answer in a single step. When you implement quantum algorithm by using the quantum oracle, the computational complexity is measured in terms of oracle queries. How many times I need to call the oracle in order to solve the problem. Okay? And in this case, because we are implementing the oracle in a quantum way, I need just one single step to apply the function f on each input and to perform the relationship, to compute the relationship between the input and output of a fancy system in a single step. Okay? So I am able to perform to associate the consequent part of a rule to the antecedent part of a rule with the proper membership degree in a single step. And when I say that the quantum fuzzy system is better than the classical system, is because its computational complexity in terms of Oracle queries is linear. Okay, so with n input variable, if my system is composed of n input variable, I need n computational steps to perform the fuzzy inference. But in the classical case, I need, by using the conventional algorithms, an exponential algorithm.
Okay, thank you very much. We're now at time for this particular webinar. I'm sorry if your question didn't ask, but I do recommend that you connect and check out obviously the conference that's coming on later this year. A webinar recording will be available, and we will request separately whether a PDF of the slides can be distributed to participants. Is that okay?
Yeah, thank you, thank you. Yes, it's okay.
And last thing before I thank you on behalf of the Computational Intelligence Society is to say lots of people are really interested in following up on your papers and seeing those links as well. So thank you very, very much.
Thank you, Kiri.
Thank you for attending. And yeah, thank you very much.
Thank you. Thank you.